In this video, we have a 3-resistor circuit where 2 of the resistors are clearly in series, that's R2 and R3, and then that series combination is in parallel with R1. So it's going to take multiple steps to simplify the circuit. I start by addressing the series combination of R2 and R3. The equivalent resistance of that series combination is 30 ohms. So just as a reminder here, I can tell those are definitely in series because the current flowing down this branch, which I'll call IR for the right-hand branch, must pass through R2 and R3. There is no other option. So if you have 2 elements that clearly are going to have the same current pass through them, those are in series. Now we redraw the circuit with the equivalent resistor. I'm going to go ahead and put in IL as the current in the left-hand branch. And we'll go ahead and call the total current in the circuit I total. So now I'm left with 2 resistors that are clearly in parallel. The high sides of these resistors are connected by wire. The low sides are connected by wire, so they're in parallel. So I'm going to use the parallel equivalent resistance formula for this. I'm just using R1 and R2 generically here. I don't mean the actual R2 from the original circuit. And I plug in my numbers and I get 1 over 47 plus 1 over 30. And I like to do this all at once in my calculator, so I'm going to type in 1 over 47 plus 1 over 30, and then I'm going to take 1 over that answer in my calculator. That gives me the reciprocal, and I get REQ out of this. So when I run the numbers, I get 18.3 ohms. And I'm going to redraw my circuit one last time. Okay, now I can start to get some things done. I have the potential difference across a single resistor, so I should be able to get the current out of this using Ohm's law. So I just write I equals V over R, and that's 1.5 volts over 18.3 ohms. And I get 0.082 amps out of this. So there's the current flowing in the entire circuit. Notice that that's going to be equal to I total in my diagram over here. So 0.082 amps is I total. And we've got the answer to part A. So I total is 0.082 amps. Now I want to get the current in each branch of the parallel part of the circuit. So that's the IL and the IR that I labeled earlier on. And to get this done, well, I'm just going to notice that I already know the voltage across each of these resistors. Each of those resistors is directly connected to the plus and minus terminals of the battery, so they have a potential difference of 1.5 across them. Then I can get the current through each of them using Ohm's law. So I equals V over R, 1.5 over 47 for this one, and I get 0.032 amps. I do the same thing on the other resistor, I equals V over R. That's 1.5 over 30, and I get 0.05 amps for that one. So the one on the left, again, I called IL. The one on the right is IR. So in part B of our question, we're asked to compute the current in each branch of the parallel circuit, verify that those currents add to the total from part A. So I found IL equals 0.032 amps, IR equals 0.050 amps, and I can see that IL plus IR is equal to 0.082 amps, and that's equal to I total. So if I talk about it in terms of the node here at the branching, all the current into that node has to be equal to the sum of the currents exiting that node, because charge can't just build up somewhere. All right, in part C, I want to find the potential difference between A and B and the potential difference between B and C, and then verify that the sum of those 2 potential differences adds up to the battery voltage. So I can see that A is directly connected to the positive terminal of the battery. C is directly connected to the negative terminal of the battery. So that's why the sum of these 2 voltage drops better equal 1.5 volts. So I've got to get some calculations done as I work backwards from my middle circuit to the one I started with. And the simplification that occurred there was the simplification of this series combination. Well, those are going to share the same current. So I'm going to write down the current through each of those. It's 0.05 amps. And that allows me to find the voltage drop across each of these using Ohm's law. So V will be, I'll call it V2. It's going to be IR. That's 0.05 times 20. That's 1 volt. V3, that's going to be given by IR. 0.05 times a resistance of 10 ohms. And this gives me 0.5 volts. And I can see the sum of those two voltage drops is equal to 1.5, the terminal voltage of the battery. So VAB, the potential drop from A to B, is exactly the potential difference across R2, and that's 1 volt. VBC, that's the potential drop across R3, that's 0.5 volts. And I can see that VAB plus VBC is 1 plus 0.5, which is equal to 1.5 volts. Good. Finally, I want the power dissipated by each resistor, and then I want the total power dissipated by the circuit by adding those together. And then I want to compare to what I get if I do the power calculation on the simplified circuit, the third one over here. So I'll go ahead and color code this in green. I want the power dissipated by each of these resistors, and I'm going to try to get the calculations done up here in my circuit diagrams. So if I look at my intermediate circuit, in that picture I already have the 47 ohm resistor solved, and I can get the power out of it really quickly. And I think just to mix things up, I'm going to use I squared R this time. Remember, there's 3 different ways of writing the power dissipated by a resistor. And that's 0.032 amps squared times the size of the resistance, 47 ohms. And I get 0.048 watts. And I'm going to call that P1 because that's resistor 1. And I'll go ahead and make a note of it down here. P1 is equal to 0.048 watts. All right, then I have to get into resistors 2 and 3. And these are completely solved as well. If I look at my original circuit diagram, I have the resistance, the current, and the voltage for each of these. So I have choices as to how I compute the power. Maybe I'll do P2 using V squared over R. The potential difference across it is 1 volt. And I end up with 0.05 watts out of this. Okay, then I look at P3, and I guess just to show all the variety that's possible, I'll use the third possible formula for power. That's IV, and I get 0.05 times 0.5, and that gives me a power of 0.025 watts. When I add all those up, I get the total power dissipated by the circuit, and to 2 sig figs I get 0.12 watts. I can also get the total power by looking at my simplified circuit that has only 1 resistor in it. And I have here that P total is, I'll just go ahead and use V squared over R for this, 1.5 squared divided by 18.3. And when I run the numbers on it, I get 0.12 watts. So that agrees with the sum of the powers of all the individual resistors, which is what we were asked to show. So we're done. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.